Let us discuss about matrices, and we review the fundamental concepts of matrices. So we know that a matrix is an array of m(n) numbers arranged in m rows and columns. So we write matrix A with elements A11, A12 up to A1n, A21, A22 up to A2n, down to AM1, AM2 up to AMN. So we can write A as Aij, where Aij represents all the elements of matrix A with I ranging from 1 up to M and J from 1 up to N. So if we are to write down the elements of the ith row, the elements are AI1, AI2, AI3 up to AIN. Similarly, if we want to isolate the elements of the jth column, that will be A1j, A2j, A3j up to AMJ. If Aij is a 3 by 4 matrix, that means that A has 3 rows and 4 columns. And it also means that there are 3 times 4 elements, or 12 elements. A matrix A is a square matrix if the number of rows is equal to the number of columns. So example, A with elements 5, negative 1, 0, and 3 is a square matrix because it has 2 rows and 2 columns, and we say that A is a 2 by 2 matrix. If A equal to Aij is an n by n matrix, the elements of the diagonal, which is sometimes referred to as the main diagonal, are A11, A22, A33 up to ANN. Another type of a matrix is a diagonal matrix. A is a diagonal matrix if Aij is equal to 0 for all I is not equal to j. So example, matrix A is a 3 by 3 matrix with elements 5, 0, 0, 0, negative 1, 0, 0, 0, negative 7. Take note that all the elements are 0 for all A's where I and J are not equal. So the non-zero elements or the elements along the main diagonal are not all 0. There could be a few zeros along the diagonal, but not all of them are zeros. And all the rest are 0. Then we also have a scalar matrix. A scalar matrix is a diagonal matrix where Aij is equal to some constant k for all I that are equal to j. So scalar matrix is a diagonal matrix, meaning to say it is a square matrix and all elements are 0 except for those along the main diagonal. And not only that, the entries along the diagonal are equal. So 3, 0, 0, 0, 3, 0, 0, 0, 3. Okay? So it's called a diagonal matrix. Now we also have an upper and a lower triangular matrix. So for an upper triangular matrix, an example of that is 3, negative 1, 2, 0, 1, 3, 0, 0, 5. Okay, you will notice that the elements Aij are equal to 0 for all I that are greater than j. This element, the first 0 here, is along the second row, first column. This is the element A21. The row number is 2 and the column number is 1. For the other elements that are 0, these are A31 and A32. Again, the row number 3 is greater than the column number 1. That is why the element is 0. For A32, the row number is 3 and the column number is 2. Again, the element is 0. And it is quite obvious why it's called an upper triangular matrix, because the elements along and above the diagonal are not all 0. So related to that is a lower triangular matrix. So an example, negative 2, 0, 0, 1, 3, 0, negative 2, negative 1, and 5. So elements along the diagonal and below are not all 0. And we say that Aij is equal to 0 for all I less than j. So take note of this element. This is the element A23. The row number is 2 and the column number is 3. And 2 is less than 3, and that must be equal to 0. Okay? Now we also have the operations on matrices. What are these operations? The first one is the sum. So if you have a matrix A, Aij, and matrix B, Bij, where I is from 1 to m and j is from 1 to n. A and B must have the same size for its sum to be defined. No? So if C is the resulting matrix equal to the sum of A and B, that means that Cij, or the elements of C, are equal to Aij plus Bij. What we do is we simply add corresponding elements. So this is negative 2, 1, 5, and 3. We add it to 5, 4, negative 7, and 1. We just add the elements correspondingly. Negative 2 and 5 will give us 7. No, negative 2 and 5 is 3, sorry. Then 1 and 4 is 5. 5 and negative 7 is negative 2. 3 and 1 is equal to 4. The second one is matrix multiplication. So we are given matrix A equal to Aij of any size and our constant R. So if matrix C is equal to R multiple of A, that means that Cij is equal to R times Aij. In other words, each element of matrix A is multiplied by the constant R. So example, if you have a constant negative 3 multiplied to 1, negative 5, 1, 0, 2, negative 3, each element is multiplied by negative 3. So we simply distribute, no? We simply distribute or multiply each element by negative 3. So the resulting matrix will be negative 3, positive 15, negative 3, 0, negative 6, and positive 9. Then we also have matrix transpose. We are given matrix A equal to Aij. The transpose of matrix A is equal to Aij transpose equal to Aji. For I between 1 m and j from 1 to n. In other words, the transpose consists of the elements of A where the row position becomes the column and the column becomes the row. So example, if A is 3, negative 2, 0, 9, 1, 5, the transpose will be a 2 by 3 matrix. No? A is a 3 by 2, so the transpose will be a 2 by 3. The first row becomes the first column, second row is the second column, and third row is the third column. Then we also have matrix multiplication. So A is Aij and B is Bij. A is an M by P matrix and B is a P by N matrix. It is important that the sizes of A and B are compatible. A is M by P, meaning to say it has P columns, and B is a P by N matrix, meaning it has P rows. So the number of columns of A must be equal to the number of rows of B for the product AB to be defined. For the product AB to be equal to C, Cij is equal to AI1 B1j plus AI2 B2j plus and so on and so forth AIP BPJ. So the ith row of A, ith row is multiplied to the jth column. The ith row is multiplied to the jth column of A. All the products are added together to form the element Cij. In a more compact form, Cij is equal to the sum of AIP, or let me use the index K, AIK, BKJ, where K runs from 1 up to P. Let us have an example. Say A is equal to negative 2, 1, 3, 0, 1, negative 2. So it's a 3 by 2 matrix. And let B be equal to a 2 by 3 matrix. Negative 1, negative 2, and 1, 1, 0, 3. 2 by 3. So we determine the product AB. Alright? So let us see if it satisfies the requirement 3 by 2 and 2 by 3. Okay? So that means that the product AB is defined. So let us rewrite the matrices. Negative 2, 1, 3, 0, 1, negative 2, multiplied to negative 1, negative 2, 1, 1, 0, and 3. We'll start with the first row, multiply to the first column. Okay, so what do we get? Negative 2 times negative 1 plus 1 times 1. So the element in the first row, first column, will be equal to 2 plus 2, or rather 2 plus 1, which is equal to 3. Alright? So the first element here will be A3. Next, we multiply the first row of A to the second column, and that will be negative 2 times negative 2 plus 1 times 0. That will be positive 4 plus 0, or positive 4. Next, still on the first row, A multiplied to the third column. That will give us negative 2 times 1 plus 1 times 3. Negative 2 plus 3 gives us positive 1. Okay, so we continue. 3, we now go to the second row, first column. So we go down to the second row and multiplied it successively to columns 1, 2, and 3. Okay, so let us do it mentally now. 3 times negative 1 is negative 3. 0 times 1 is 0, so that will be negative 3. So second row to the second column. 3 times negative 2 is negative 6. 0 times 0 is 0, so it will be negative 6. We are now up to the third column. 3 times 1, 0 times 3 is 3. So third row of A, we go down to the third row, multiply to the first, second, and third columns of B. So 1 times negative 1 is negative 1. Negative 2 times 1 is negative 2. Negative 1 and negative 2 is negative 3. 1 times negative 2 is negative 2. Negative 2 times 0 is 0. So negative 2. And finally, 1 times 1 is 1. Negative 2 times 3 is negative 6. 1 and negative 6 is negative 5. Let us also determine the product BA and see what will happen. So B is negative 1, negative 2, 1, 1, 0, 3. And A is negative 2, 1, 3, 0, 1, negative 2. So first row to first column. Negative 1 times negative 2 is positive 2. Negative 2 times 3 is negative 6. 1 times 1 is 1. So 2 minus 6 is negative 4. Plus 1 is negative 3. Next, first row, second column. Negative 1 times 1 is negative 1. Negative 2 times 0 is 0. 1 times negative 2 is negative 2. So negative 1 plus 0 plus negative 2 is negative 3. We go down to the second row of B, multiply to the first column of A. So 1 times negative 2 is negative 2. 0 times 3 is 0. 3 times 1 is 3. So negative 2 plus 0 plus 3 is positive 1. And finally, second row of B to second column of A. 1 times 1 is 1. 0 times 0 is 0. 3 times negative 2 is negative 6. So 1 plus 0 plus negative 6 is negative 5. And from this example, it is very clear that the product AB is not equal to the product BA. So we can generalize that matrix multiplication is not commutative. Okay, so the product AB is not equal to BA.